Assalamualaikum warahmatullahi wabarakatuh and good afternoon to everyone. How are you? I hope you all are in good health. Alhamdulillah, I'm fine. So today we will, from chapter 3 onwards, okay, I plan to conduct the class asynchronously so that this is based from feedbacks that I've received in last lecture. So most of you prefer asynchronous so that you can learn at your own pace. Yeah. So let's give it a try. So today we learn new chapter, angle modulation. Okay. Yes. All right. So before I start with the content itself, I just want to share a number of three final year exam questions on FM or angle modulation. Okay, so why I want to do this? So that you can be alerted when these terms come out in our during the lecture. So throughout the lecture, if you come across some of the terms, then you can pay more attention because you know that they are actually important and have come out in final year exams. Okay. So first we look at this question, 2018-19 semester 2. So PM and FM, often collectively known as angle modulation, to determine whether the signal is FM or PM, bandwidth test using sinusoidal signal is conducted. So the resulting bandwidth are tabulated below. So the resulting approximate bandwidth of the angle modulated signals are tabulated below. So this is our table for three different set of experiments conducted on the same system, categorized if the system is narrowband or wideband, FM or PM. So here, okay, we can notice the terms like FM, PM, and wideband FM, narrowband FM, bandwidth, approximate bandwidth. Okay, so I hope you can pay attention during the lecture, wherever they're mentioned. So for this final exam, I'll just focus on the first part, on the introduction to FM. So from general equation up to power performance. Okay, so the second one shows, this figure shows FM spectrum. You can see, so you can compare to AM that has maximum 2 sidebands. We have many sidebands. We can have many sidebands in FM. Okay, and then what the question asks are very similar to AM modulation index, the time domain expression of the waveform. So this is something new. Maximum frequency deviation and maximum and minimum instantaneous frequencies. So what are they? And then session 2019-20 semester 1. So we are given information on the carrier and also information signals and also the frequency sensitivity KFM. So here we have a new parameter or new term, frequency sensitivity. We don't have this in AM. Right expression determine the bandwidth using Cousins. Okay, so calculate bandwidth, but now we have this new word Cousins rule. So in FM, there is a specific method to calculate bandwidth that is different from AM. Okay, and then last semester described the methods of principles of demodulating frequency FM signal. So you know that actually there is not only one, so at least there should be two based on this question. And then a given FM signal, explain narrowband. Okay, so again, previously we had question already asking to categorize whether it's narrowband or wideband FM. Here, again, definition of narrowband FM, wideband FM, and proof equation for narrowband. Okay, so that's it. So you can see from the first parts of these three, from these three final exams, the first part of FM, the introduction parts, covered in overall almost the same thing. Yeah, general equation, spectrum, bandwidth, but there are also some new things that are added. Okay, for this part one, what I want to touch, I'll just give the overview for today's lecture. Okay, first we start with general equation. So since angle modulation actually comprises PM, phase modulation, and also frequency modulation. So in this general equation, we learn about both of them. Okay, the general equation for FM and PM. Okay, in general equation, even for AM, we have the carrier and information signals. That the properties of them, these two signals like EC, EM, right, FC, FM. So similar thing with this general equation. We have also those properties, and we have also modulation index, beta. But for FM, sorry, for angle modulation, the symbol is different. It's then AM is beta here, and beta for FM is also different from PM. You can see how they are different. FM is KFEM of FM. PM is KPEM. So we have this constant, sensitivity constants, that is different between FM and PM. So FM is known as frequency deviation constant. PM, phase deviation constant. Okay, from beta, we can also differentiate whether our signal is actually narrowband or FM or wideband. So this depends on the value of beta, whether it's much less than 1, whether it's nearly to 0 beta, or much larger than 1, or much larger than 0. So if it's a very small value, it's known as narrowband FM, large values, wideband FM. Okay, from our beta, so in angle modulation, we have this a table known as the Bessel table. So I'll show you later during the lecture. So in Bessel table, you're given, when you're given beta, it shows the number of sidebands n for a given beta. And not only the number of sidebands, it also has the normalized amplitudes of the sidebands. What are the amplitudes of the sidebands in reference to EC, carrier's amplitude? Okay. So we learn about spectrum, and we also learn about bandwidth. Okay, but in FM there are two approaches to measure bandwidth. First is the actual bandwidth, Bessel, and another one is the approximate bandwidth, Carson. Okay, so for Carson, this is an approach to have more efficient use of bandwidth, but not compromising the power performance. Okay, and next we also have the power for our angle modulation. So this is the first part, overview for the first part. And the second part of chapter 3, okay, this will be covered inshallah next week. Okay, so it's very similar in terms of the overall flow from generation, detection, and practical FM receiver. Similar to AM, we also have the direct and indirect methods for generation and detection. But for generation, we have additional topic, which is how to generate wideband from and narrowband, right? From narrowband to wideband. And then for practical FM receiver, apart from super heterodyne, so this concept of super heterodyne is similar to AM. Okay, but we have also additional topic known as FM stereo. Okay, so this is for second part of our chapter 2. Okay, so let's start with the basic concepts of FM. Okay, so we learned about AM in previous chapter, but actually there's also another well-known modulation technique known as angle modulation. So in angle modulation or exponential modulation, the modulating signal changes the carrier's frequency and phase. Okay, so remember in AM, the modulating signal changes the carrier's amplitude, but angle modulation, so as what the name implies, changes the carrier's angle, and this angle, theta t, actually comprises of frequency and phase. It was introduced by the scientist Edwin H. Armstrong. So from the general signal expression here, A is our amplitude, theta t is our angle, we can actually change the carrier's amplitude or angle in order to send information. So we have learned how the modulating signal changes the carrier's amplitude. In this chapter, we learn how modulating signal changes the carrier's angle. Okay, so let's look how actually we can vary the carrier signal's angle. Okay, so angle of a sine signal is given as this theta t, which is equal to omega ct plus theta naught. So theta naught, okay, is the initial value of our theta t at t equal to 0. Okay, so in AM, our theta naught is equal to 0. So that's why in AM, we just see the angle is just cos omega ct. Okay, because we don't pay attention on the angles changes. So we just stick with omega ct, assume theta not equal to 0. Okay. If we have a specific value of our theta naught, then it will not start at 0. But it has a linear relationship. So the linear line of our angle is given by this blue dotted line. So it's omega ct plus theta naught. Okay. So the gradient of our theta t, if we take the gradient, is actually equal to omega c, which is the carrier signal's radiant frequency. So from here we can see the relationship between carrier's angle and carrier's frequency, which is the gradient of our angle is our frequency. Okay, so this is when our omega c is fixed. You can see when gradient for this linear graph, the gradient is fixed, so the omega c is also fixed. Okay, omega c also fixed. But we want our frequency to change. So the gradient then also have to change. So this red line shows a relationship where the gradient or the frequency of our signal changes with time. So it can be represented by this red line known as theta xt. So this is where our signal follows non-linear process, and the gradient represents the instantaneous angle frequency omega I. Okay, so at time you can see that when both of them are similar, and the blue and the red lines, the instantaneous frequency at this interval time is also equal to omega c. Okay, so at other times, the instantaneous frequency at that interval is actually equal to gradient at that particular interval. Okay, so the instantaneous angle frequency at time t is by calculating the gradient of the graph at time t as well. So the instantaneous frequency is equal to the gradient of our angle, theta t, which is, can use the symbol theta t with dot on top. So, or the first derivative of our theta t. So the instantaneous angle, from this relationship, can have the inverse equation. So theta t is then equal to integration of our instantaneous frequency. Okay, so these two are very important. So you need to understand instantaneous angle, instantaneous frequency. So this omega I is instantaneous angular frequency. Okay, if it's just instantaneous frequency, it's Fi. Okay. Okay, so from that previous slide, can show that our VMT can be transmitted if the amplitude of the carrier is held constant, but the angle, whether phase or frequency, is varied linearly with the VMT or VMT. Okay, so assuming our VCT is equal to EC cos omega CT plus phi CT, where this part in brackets is actually our angle theta t. So the instantaneous angle value is theta CT equal to omega CT plus phi CT. Okay. So the instantaneous angular frequency omega IT is equal to differentiate. We differentiate our angle, so it becomes omega C plus the first derivative of our phase deviation. So this part phi CT is the phase deviation, because our omega C is actually fixed. It's a reference frequency of the carrier. Okay, so this is where we start. And the phi CT, okay, see, the phi CT here is the part where our VMT, where the phase deviation part here is the part that is changed due to our VMT. Okay, so this is the part that will be changed. Okay, so this is same as previous slide. Instantaneous frequency is omega C plus the frequency deviation. The instantaneous angle is equal to this omega CT plus the phase deviation part. Okay. So you have to take note and all the terms. This is instantaneous frequency, instantaneous angle, reference frequency. This is frequency deviation. This one, and the one below, this one is the phase deviation. Okay. Okay, we look at the first general equation for PM. Okay, so PM implies that the phase deviation of the carrier, phi c, is proportional to our modulating signal, VMT. Okay, so our phase deviation, phi c, okay, is proportional to our VMT. So you can equate it as Kp VMT. Okay, so here, what is the unit of our phase deviation? It's radians. Okay. So since this is in volt, so in order to make it consistent, the unit, so this one should be in rads per volt. Okay. So this is known as phase deviation constant. So from our general equation, EC cos theta t, where this is the instantaneous angle, theta t then is equal to, okay, from here, from the equation here, theta t is then is omega ct plus kp vmt. So this is the general equation for phase modulation, VPMT. Okay, let's look at the general equation for FM. Okay, for FM, so the one that changes proportional to VMT is frequency deviation. It's not phase deviation. So first derivative of our phi CT is proportional to our VMT, then is equal to KF VMT. So what's the unit here? It's rads per second, right? It's frequency, radian per second. So this one in volt. So that's why your KF has to be in rads per second per volt. Okay. So you have to take notes. The unit is different between KF and KP. So in order to put inside our general equation is C cos theta T. Okay, so we have to integrate, right, our instantaneous frequency here. Yeah, since instantaneous angle is equal to integration of our instantaneous frequency, right? Yeah. So then we integrate our omega IT here. It becomes omega CT plus KF integration VMT dt. Okay, so from here it comes here by integrating. Okay. We have to integrate first. So that becomes angle before we put inside our angle here. So okay, so this is integration. Then from here, angle put inside here. So it's EC cos omega CT plus KF integration VMT dt. Okay, so this is the general equation for FM signal. Okay, let's move to the next slide. Next, we look at the relationship between PM and FM. Okay, so they are closely related, where we can generate FM signal by using PM modulator and vice versa. Okay, we know that for FM, the VMT has to be integrated, but for PM, the VMT does not have to be integrated. It is as it is VMT. So if we use PM modulator to generate FM, of course we need to have integrated in front, so that our output will have integrated VMT. If you use FM modulator to generate PM, we have to put differentiator, because FM modulator will integrate our VMT. So in order to neutralize, keep it to the original VMT, we have to put differentiator. Then our output will not have integration at front. Okay, for the demodulation part, the process is inverse. Okay, if we use PM demodulator to demodulate FM, we need differentiator. So because PM demodulator will not differentiate our VMT. So that's why we need differentiator. If we use PM demodulator, sorry, for PM demodulator, if we use FM demodulator, we need integrator. Because it will differentiate our VMT at FM demodulator here. So that's why we need to integrate so it becomes VMT. Okay, so from this relationship, we know that they are very closely related between FM and PM. Okay, so throughout our next lecture, we'll just focus on one type of angle modulation technique, which is FM. Okay, so I'll stop here in this our part 1 video, and in next part I will continue with the more details on FM analysis. Okay, see you in the part 2.